Hi everyone, welcome back. So in this video, I'm going to discuss about the TCP header. You know about the transmission control protocol. So let's talk about what are the contents that are there in the TCP header, what are their functionalities. Okay. So first things first, in transport layer, usually the two most common protocols that are used are the UDP and the TCP. UDP stands for User Datagram Protocol. TCP stands for Transmission Control Protocol. So TCP is connection oriented and it is reliable. UDP is connectionless and unreliable service. If you're wondering if there is TCP, why do you want to have another protocol UDP in transport layer? That's simply because not all the applications require the reliability of TCP. Some of them desire the delay sensitive. There might be some applications which are delay sensitive. For those kind of applications, UDP suits best. So as I told you, transmission TCP, in other words, is also called as transmission control protocol. It stands for, it is a connection oriented, reliable protocol. And obviously, because it is a connection oriented protocol, it has to provide all the connection oriented services such as detection of packet losses, no packet duplications are allowed. So acknowledgements, delivery, guarantee of delivery. So for all of those things to happen, the sending TCP must be in communication with the receiving TCP. For that purpose, you can see the header of TCP, which is shown on the slide here, which contains all the details that is used by the TCP protocol to ensure all the connection oriented services it provides. You must have seen the UDP header, which is very simple when you compare it to this more complicated TCP header. As usual, let me just discuss the outline of this header. Then I will go into details about what each field does in this particular header. First things first, in transport layer, all the protocols or the particular processes are identified by their port numbers to which they are attached to. So hence both the UDP and TCP always start with the source port number and destination port number. Both of them are 16 bits in length. You can see these are the first two fields. One of them is the source port address and the other one is the destination port address. After that, we have the sequence number, which is 32 bits in length. Then we have the acknowledgement number, which once again is 32 bits in length. Then followed by the header length field, which is of 4 bits. This is a reserved field of 6 bits, which is not currently in usage and which is left for any kind of future purposes. Next comes this field is called as the controlled field, which consists of 6 flags. You know what is a flag? It's either yes or no, true or false. It's just 1 bit. Okay. We will discuss the functionality of each one of these flags in detail. Next follows the window size field, which is once again 16 bits in length. Next comes the checksum field to give you the error control functionality. And then comes the urgent pointer, which is once again 16 bits in length. Now, the next two fields, which are options and padding, and then the data, which is all optional. These two fields are actually optional in TCP. They might be there or they might not be here also. Okay. These are the optional ones. So usually when someone asks you what is the size of a TCP header or TCP segment header, you have to mention it is anything between 20 to 60 bytes. So what do you say? Where did you get these numbers? If you see, the length of this particular one is 32 bits, right? So these fields are mandatory. So 1, 2, 3, 4, 5. So 5 32s are 160. So the first 160 bits are mandatory for any TCP header. So which gives you the minimum length of the TCP header is 20 bytes. 20 bytes means 160 bits. So these are. Next follows the options field, which will add a little bit more information to this. So this is optional. If any source or source and destination machines want to convey extra information, only then these are added. Otherwise, these are not added. So this you can have up to 40 bytes. You can have up to 40 bytes. So you add this 20 to 40, which gives you the maximum size of the TCP header is 60 bytes. Then comes the data part, which is an optional one. Okay, that means some of the TCP segments might not have any data in them. because this is when we use it for connection establishment. Those kind of packets or segments do not have any data in them, so it's an optional. You have to remember that it's not mandatory that each and every TCP packet contains the data field. Okay, so the minimum length is 20 bytes, the maximum length is 60 bytes. So if somebody asks you what might be the size of the data, you have to calculate it as 65,535 bytes minus 20 bytes for the TCP header minus 20 bytes for the IP header. Okay, so which gives me 65,495 bytes. This might be the maximum value of the data field that you can have. Okay, so getting back, you know that TCP is a byte-oriented protocol. Byte-oriented protocol means it does not maintain the message boundaries during transmission. So it simply gathers the data, puts them into bytes, packs them up, and sends them to the receiver. Now, there is a misconception that when I say it's a byte-oriented protocol, most people will think TCP does it do the transmission in single bytes. No, it does not. It's an intelligent protocol. What it does is the sending TCP waits for good number of bytes, sufficient enough to fill maybe one packet size or one decent packet size, and then transmits this particular packet to the receiving machine. And most of the people think that because when I say this byte-oriented protocol, only a single byte is transmitted per segment. No, the sequence number consists of the first byte number. In TCP, because it is byte-oriented, each and every byte has a sequence number attached to it. Well, we will discuss about the sequence number. Now, what is the segment? Each packet in TCP is called as a segment. You can see the host TCP buffers enough bytes to fill a reasonably sized packet and then transmits this packet to its peer on the destination host. Okay, so just the key points to remember are the minimum size of the TCP segment header is 20 bytes. The maximum segment header size is 60 bytes. Now let's move on to discuss the individual fields in detail. Now, first things first, as I told you, the first two fields are your source port address and destination port address. If you remember correctly, transport layer uses port numbers, your network layer uses IP addresses, your data link layer uses MAC addresses to identify the machines and processes. So similarly, both these fields do help to establish the connection. So this is a 16-bit field that defines the port number of the application program in the host that is sending this segment. So you can see this is the source port address, which tells you which application on the source machine is transmitting this segment. And similarly, the destination port address will tell you to which application program should this segment be delivered at the destination machine. Okay, so now with these two, the TCP port plus its host IP address forms a 48-bit unique endpoint called the socket. So what is this socket? A socket is nothing but the combination of the IP address, which is 32 bits, and the 16-bit port address. Okay, so both of them you add, you get the 48-bit socket address. So sockets are nothing but the endpoints of communication in networks. So those source and destination endpoints together identify the connection. So this connection identifier is called a phi tuple. Why do we call it as phi tuple? Because it contains 5 identity information. What are those information? The first one is which protocol are we using? Is it TCP or UDP? So the first information is the type of the protocol. Which protocol are we using? The second one is the source IP address and the source port address. And the fourth one is the destination IP address and the destination port address. So all these 5 pieces of information together can identify your connection. So hence we call it as a phi tuple. So after this field, next we have the sequence number field. So the 32-bit field defines the number assigned to the first byte of data contained in this segment. Each byte in TCP is numbered. So let me give you a small example to tell you that. Let me say that I have maybe, let me say 5,000 bytes of data to be sent. Okay, 5,000 bytes of data that is to be transmitted. So the numbering will be between 0 to 4,999, right? Now, if I package them into 1,000 byte segments each, so in the first segment, what will be the sequence number? Usually zero sequence number will be going to the sequence number bit, or the synchronization part, or for the connection establishment part. So the first sequence number here will be, let me assume that, let us say that is 2 or 3. So 2. So this 2 mentions that the first sequence number, or the sequence number assigned to the first byte in this segment. As I told you, each segment is 1,000 bytes, right? So the last byte number will be 999. In the second segment, the sequence number field will contain the value 1,000, because 1,000 is the first byte in this segment. So here you can send until 1,999. For the third segment, the sequence number will be 2,000. So in this way, the sequence number always corresponds to the sequence number of the first byte in your TCP field. Okay, so here the maximum number it is permitted is 2 power 32. So once it reaches 2 power 32 minus 1, it will automatically wrap around back to 0. So this is the sequence number field. So remember that because TCP is connection oriented and byte oriented protocol, you have to keep in mind that each and every byte that is transmitted in TCP will have a sequence number attached to it. Irrespective of sending the sequence number of each byte present in the packet, I'm just writing the sequence number of the first byte. That's all. So each and every segment, this sequence number field corresponds to the sequence number given to the first byte in that packet. Okay. So automatically after this field, we have the acknowledgement number field. So the acknowledgement number field is also 32 bits in length. If you remember the concept of piggybacking, where the receiver can wait for a particular bit of time to attach the acknowledgement to the next outgoing frame. This field is attached for that particular purpose where piggybacking can be done. So this acknowledgement number is also called as a cumulative acknowledgement. Let me tell you what is this. Now, if I am the receiver and if I have received the first segment earlier that we discussed with the number as 999, now I will send the acknowledgement number as 1,000, because I always send the acknowledgement number which is equal to the sequence number of the next byte that I'm expecting from the sender. Let me just explain it a little bit better. So the sender sends the first segment, which consists of 1,000 bytes, and the last sequence number in that particular segment is 999. So what will be the next byte? What will be the next sequence number of the byte? 1,000. So the receiver now sends an acknowledgement which tells the sender that, hey guys, this is the sequence number I'm expecting next. Okay. So in this way, see, after 999, the acknowledgement number will be 1,000. This will be sent only if this particular segment is received without any errors. Okay. Now let us assume that the second segment is also received perfectly by your receiver. It has been received without any errors. So what will the receiver do? Now it will send an acknowledgement of 2,000, because the last byte here is 1,999. The acknowledgement number will be 2,000. So it is telling the sender that the next byte which I am expecting is 2,000. And also remember, we call this as a cumulative acknowledgement simply because if I am sending an acknowledgement number of 2,000, it automatically tells the sender that all the bytes starting from 0 to 1,999 have been received correctly. There are no errors with these bytes. So all the sequence numbers of the earlier bytes have been received without any errors. Successful transmission is done. That is why we call it as a cumulative acknowledgement. You can see it is a cumulative acknowledgement because it summarizes the received data with a single number. So if I'm sending acknowledgement number as 2,000, which means that the first bytes starting from 0 to 1,999 have been successfully transmitted. So acknowledgement and data can be piggybacked together. Now, sometimes there might not be no acknowledgement at all. In that case, this acknowledgement number has no value. Now we will show how a receiver distinguishes between a valid acknowledgement number and an invalid acknowledgement number. Now, next comes the field which is called as HLN, which stands for header length. As I told you earlier, the minimum length of the TCP header is 20 bytes, right? And the maximum length is 60 bytes. So this field tells the sender what is the length of the header. So this field refers to the header length. This is a 4-bit field. That means I'll have only 4 bits, right? 1, 2, 3, 4. 4 bits. The maximum value which I can show with these 4 bits is 15. Right? Because all ones, if I put all ones here, the maximum value that I can showcase with these 4 bits is 15. So the minimum length of the header length field is 5. Sir, where did you get this 5 from? This 5 I got it from, because the minimum length is 20 bytes. This 4-bit field indicates the number of 4-byte words into 4. So 5 into 4 gives me 20 bytes. And sir, what is the maximum length? 15. So 15 into 4 bytes gives me 60 bytes. Okay. So the header length value can be anything between 5 and 15. If it is less than 5, then the segment is a error one. It contains some kind of errors. It is not done properly. So if anybody asks you what is the minimum length of the header length field, it is 5. Because this 5 corresponds to the number of 4-byte words. So 5 into 4 gives me 20 bytes, which is the header length. And if I have 15, which tells me that the value of the total length of the header is 15 into 4, which is 60 bytes. So therefore, the value of this field is always between 5 and 15. Okay. So next comes the reserved field, which is of 6 bits in length, which is left for your future purposes, which is not used currently. So let us discuss this control field in detail. So what are those that are there in this particular one? And you might be wondering, sir, you shown us 6 flags, but here there are 8 flags on display, right? Yes. The thing is, these are the original flags that we displayed earlier. These are the flags which we displayed 1, 2, 3, 4, 5, 6, right? These are the 6 flags that make up the control field. But in some of the bibliography and some of the references that I found on the internet, recent editions of TCP have included these 2 flags for congestion control purposes. So I will discuss those 2 also, but I will leave it to you guys. If you want to just mention those 6 flags, the original 6 flags only, fine. But if you want to add these 2 also, it is also fine. So the control field defines 8 different control bits or flags. 1 or more of these bits can be set at a time. So these bits enable flow control, connection establishment and termination, connection abortion, and the mode of data transfer in TCP. So usually these flags allow you to do the connection establishments, maintain flow control and even congestion control and connection termination, even if you want to abruptly end an connection, and also say convey additional information to the sender. So let's discuss about each one of these flags in detail. The first 2 flags, which stand for congestion window reduced, CWR stands for congestion window reduced, and ECN stands for explicit congestion notification. Explicit congestion notification. Okay. I'll show you. I'll underline these things. You can see this now. So what are these 2 used for? You know, in congestion control, there is a concept called as explicit congestion control. If a particular host on the connection is facing congestion issues, it needs to convey that information. So for that purpose, what it will do is it will put a 1 here. It will put a 1 here, because you know that these are all 1 bit. The flag means it's either 1 bit. That means it's either true or false. It's just of 1 bit, 1 or 0. It puts a 1 here. That means this is set actual to signal an echo, ECN echo, to a TCP sender to tell it to slow down when the TCP receiver gets a congestion indication from the network. So the receiver is going to tell the sender that it is facing congestion, that it is called as ECN. ECE means explicit congestion echo or ECN echo. Now, once the sender receives this one bit, where receives the acknowledgement with this bit as set as 1, it will understand that the receiver is facing issues. So what it will do is it will reduce its congestion window. That means it will reduce the number of segments that it is sending. And to convey that information to the receiver, that means it has to tell, okay, guys, I acknowledged your transmission, that I know that you are facing congestion. Now I am going to slow down. For that, what it will do is it will set a 1 here, CWR, congestion window reduced. So CWR is set to signal the congestion windows are reduced from the TCP sender to the receiver, so that it knows the sender has slowed down and can stop sending the echo. So this process will continue till the receiver is alleviated of its congestion problem. Once the congestion is gone, this bit will be reset to 0. And once it is reset to 0, this sender will stop reducing its congestion window and it will set as a 0. So these two fields will enable the sender and receiver to discuss or to communicate regarding congestion. If a receiver is facing congestion, it will set this ECN bit as 1, which will tell the sender that your receiver is facing an issue and hence you slow down. Once the sender acknowledges this and slows down his transmission, it has to convey this information to the receiver. So for that purpose, what it will do? It will put a 1 in the congestion window reduced. This process continues till the receiver gets out of its congestion issue and marks the ECN as 0. So these are the two flags that are used for establishing congestion control. So CWR stands for congestion window reduced and ECN stands for explicit congestion notification. I'm talking about ECE also. ECE is nothing but echo, ECN echo. Okay. Now let us go a little bit further to the first bit, which is called as URG. URG is set to 1 if the urgent pointer is in use. So what is this urgent pointer, sir? In TCP, there is a how do I say it? There is an capability to prioritize the data that you are sending. Now, if the receiving applications needs a data or immediately for interrupt purposes or something like that, your sender can convey this information to the receiver by using these two things. So if URG is set to 1, automatically, which means that you have to go to the urgent pointer field to find out where the urgent data is present in your segment. How do you do that? So let me say that your sequence number starts from 2 in your segment. In your segment, your sequence number starts from 2. And the urgent pointer has a value of 300. Your urgent pointer has a value of 300. And if I'm setting URG as 1, it will tell the sender or it will tell the receiver that starting from 2 till 300 bytes, all these bytes are urgent data and please give it to the receiver. So this urgent pointer points to the offset starting from your starting sequence number. All the data are urgent data. Okay, so URG is set to 1. The urgent pointer is used to indicate a byte offset from the current sequence number at which urgent data are to be found. So this is how you find it. So URG is set to 1, but this option is no longer being used in any of the modern TCP implementations. This is an old version. Okay, so but remember that in order to prioritize data, you can use the urgent pointer. If you are having any urgent data in your segment, you simply set the urgent flag to be 1. And if it is set to 1, automatically you have to go to find out, to tell the receiver where the urgent data is present, go to the urgent pointer, find out the offset, what it is there, calculate it from the current sequence number. Okay. The next one is acknowledgement. As I told you, not each segment has an acknowledgement number, has a valid acknowledgement number, but acknowledgement number field is mandatory. So if there is, how does the receiver identify that the received acknowledgement number is valid or invalid? For that purpose, you have an acknowledgement flag or this bit. So if the acknowledgement number is valid, you put a 1 there. So when the receiver receives this control field and it will see a 1 here, it will automatically consider the value in the acknowledgement field, which is 32 bits in length. If it is a 0 here, it will know that, okay, the acknowledgement field is not valid and it will not consider the data. So this acknowledgement field or this acknowledgement flag is used to tell the receiver whether this segment contains a valid acknowledgement number or not. The next one is push data, PSH. So this indicates push data. Why we need to have this is TCP's receiver has a buffering system. So when you're sending the segments, it will not immediately deliver it to the receiving application. Based on the size of the segment, it might put it into a buffer and wait for the buffer to fill up to some certain point. That means the packet has to be a reasonably good size so that it can forward the entire packet to the application process on the receiver. Sometimes this cannot be done for applications which are delay sensitive or which need to send the data immediately. For that purpose, if the sender marks this push bit as 1, it is going to tell the receiver that do not buffer this particular data and forward it to the receiving process as soon as you receive it. So when the push bit is set to 1, the receiver TCP, what it will do is it will not place this segment into the buffer and it will immediately push it or give it to the receiver's application process. So the receiver is hereby kindly requested to deliver the data to the application upon arrival and not buffer it until a full buffer has been received. So don't buffer it, just pass it on to the receiver. That is, we call it as push bit. Next comes the reset bit. So if there is an issue, maybe a host crash or some other reason, invalid number coming, and if you want to reset a connection, either the sender or the receiver will send a TCP segment with the RST bit as set to 1. Okay, this is used for resetting a connection. The next two bits or the next flag bit is called as SYN bit or the synchronization bit. This bit is used specifically for connection establishment process. If you are sending a packet with SYN is equal to 1 or SYN bit set as 1, it means that the sender is requesting for connection establishment with the receiver. Okay, the connection request has SYN is equal to 1 and ACK is equal to 0. The connection reply does bear an acknowledgement, however, so it will have a SYN is equal to 1 and ACK is equal to 1. So by using this SYN field and ACK field, usually you establish the connection in TCP via a process called as three-way handshake. We call it as three-way handshake model for TCP connection establishment. We will discuss that particular process and the usage of these bits for successful connection establishment in our next video. The last flag, which is called as FIN, which is used to, or in other words, it is finish. If a sender he wants to convey to the receiver that I am done sending all the data, my job is finished, then it will send this particular FIN bit set to 1. This is used for connection termination. So the FIN bit is used to release a connection. It specifies that the sender has no more data to transmit. So these are all the flags. So CWR stands for congestion window reduced, ECN stands for explicit congestion notification, and URG stands for urgent data. ACK stands for acknowledgement is valid or invalid. Push data or push PSS stands for push data, whether the receiver needs to push this data immediately or it can put it into a buffer. Reset stands for if any machine wants to reset a connection because of some issues. SYN bit stands for connection establishment or synchronization request, and FIN or finish stands for the sender conveying to the receiver that it has no more data to send and you can now release the connection. So this is the controlled field of TCP. As I told you, some of the books you have only these 6 flags, and in some of the modern textbooks I came across these 2 flags also, which are added to provide the congestion control service by the TCP protocol. Okay, now let's move on. The next field is something called as the window size field. It is also once again 16 bytes in length, sorry, 16 bits in length. Now, what is this window size? You can simply say that TCP does also provide flow control. So what is flow control? Flow control ensures that the sender only sends the data requested by the receiver at a rate acceptable by the receiver. So if a receiver says, guys, I have only space for 100 bytes, the sender can only send 100 bytes. If the receiver says, I have only space for 500 bytes, the sender has to send only 500 bytes. Now, how does the receiver convey that? This is the field. So the window size field is actually determined by the receiver. This field conveys to the sender how much data it can send now. Usually this field corresponds to the buffer size present at your receiver side. If a receiver side has whatever buffer size is left, it will convey that information to the sender, so that the sender will only send that particular amount of data only. Under no circumstances, the sender is permitted to send more number of bytes than advertised by your receiver. Hence, flow control is ensured in TCP. That is what flow control is about. I don't want the sender to send as much data as it wants without regards to the receiver's capability. So only when the receiver asks for the data, your sender will send it. So the length of this field is 16 bits, normally referred to as the receiving window or RWND. We will discuss about these window sizes once again during the congestion control part of TCP, and issued to indicate the number of bytes that can be accepted at one time by the receiver. So a window size of 0 is also legal. What does it mean, legal? So sir, you can ask me, sir, you just told me that whichever window size is advertised by the receiver, the sender will only send that many number of bytes. Then why are you talking of 0 is legal? It means that the receiver's buffers are full and it cannot accept any more data at this moment. So it will send an acknowledgement number, and also it will say that my window is full, guys, please do not send me any more data. For that purpose, it can advertise a window size of 0. That means the sender can no longer send any more data. Till what time? Now, once the buffer is cleared, this receiver will send another segment with the same acknowledgement number, now advertising whichever buffer size is left over. Okay, so the receiver can later grant permission to send by transmitting a segment with the same acknowledgement number and a non-zero window size field. Sir, where did you get this non-zero number field from? Now, the difference between these two is when the receiver's buffer is full. Let me say that I have a buffer of 1000 bytes. Okay, so I have received all these 1000 bytes from the sender, but unfortunately, I'm unable to read these 1000 bytes and process it to the application layer. So I will ask the sender to wait for now. So in that at that particular time, what I do, I will send a segment acknowledgement. Send acknowledgement is equal to 1001 because I have 1000 bytes already, and I'll say window size is equal to 0. So the receiver knows that okay, all the bytes are sent correctly and the receiver has no space, so it will wait. So maybe after some time, these 1000 bytes are read to the application process. Now the buffer is empty. So what will the receiver do? It will once again send another segment. Acknowledgement is equal to 1001, the same acknowledgement number, but now the window size is equal to 1000. That means it is now permitting the sender to send another 1000 bytes. Okay, so this is the role played by the window size field. This is used for ensuring the flow control between the sender and receiver. Okay, so in this way, the receiver will tell the sender how many bytes of data to send. Only then the sender can transmit. The sender cannot regard this window size field, and it cannot send as much of data as it wants. The next field is your checksum field. You know that TCP ensures error control. That means any errors that are there, it will be identified by TCP. So for that purpose, we have the checksum field. So this checksum field is once again a 16-bit checksum, and which is in the same way that we calculated earlier. You can refer to my earlier videos for that. I did some examples on checksum also. So this 16-bit field contains the checksum. What it does, it checksums the header, the entire header, the data, if there is a data portion, it will be adding up all that data, and a conceptual pseudo header in exactly the same way as UDP. Now in UDP also there is a checksum field, but in UDP the checksum is not mandatory, it is optional. If you want, you can implement it. If you don't want it, you need not. But in TCP it is mandatory. So checksum is mandatory in TCP, and it will also include this, what we call it as a pseudo header field. So this pseudo header contains the information which pertains to the source IP address, destination IP address, your protocol field, and your total length in 16 bits. The only difference between this header and the UDP header is, for TCP, you have the bit protocol field as 6, and for UDP, it is 11. That is the only difference. And the another difference is, in TCP, checksum is mandatory. In UDP, it is not mandatory, it is an optional feature. But The checksum not only just contains all these fields, but also it should contain the pseudo header as well. If you ask me, why sir, why do you want to add the pseudo header here? Simply because it has to ensure not only just the port numbers are correct, but also the message has been delivered to the right machine or not. Both the IP addresses also should be matched. Your source IP address must be correct, and your destination IP address also must be correct. And also it must ensure that indeed the protocol used is TCP. That is the reason we have this pseudo header calculated for your checksum. Okay. The last field is your options field. I told you that the minimum length is 20 bytes and the maximum length is 60 bytes. So in between you have, or you can have, up to 40 bytes of options present. The name itself tell you these are options. That means they are not mandatory. If you want, you can add the options. If you need not, you need not have. If you ask me, sir, why we are bothered about options? Because these options convey additional information to the designation or to the destination, or align other options. Now, some of the common options that are used are your maximum segment size. That means both the sender and receiver will specify what can be the maximum segment size that is acceptable for this particular connection. They can convey that. So if I'm saying that I can only accept maybe 1500 bytes at a time or 5000 bytes at a time, I have to convey that to my source through this particular option, the maximum segment size. Okay. And the other one is timestamp. The other one is window scaling, end of options, no operation. There are many options that are available for TCP. I found quite a bit of information on the IANA website. If you're interested, you can go to that website. It has got a detailed list of all the options, how they are actually formatted, what is the size of each options. So each option has a type, length, and a value encoding scheme attached to it. So if you want more information about the options, you can go to the IANA website, where you have good enough information to discuss each one of these options in detail and what their functionality does, or what their functionality is with respect to the overall TCP's function. Okay, so with that, we come to the end of this video. Hopefully you understood the concepts of TCP header and the fields present in the header and their respective functionalities. This is quite an important one. As I told you, when you compare it with the UDP's header, UDP header is quite simple, whereas TCP header is much more complicated, because it has to provide all the services related to your connection oriented services. So with that, hopefully you did understand. Thank you very much, and do take care. Thank you. Do share and subscribe.